Okay, everyone. Today we're going to cover chapter 10, which is energy and work. Okay, so here we're going to introduce another concept, which is energy and work. So for work, in physics, when we talk about work, it's completely different from um, um, the concept of work in daily life. In daily life, when we are talking about work, we mean a job. However, in physics, work means completely different thing. It's related to energy. Now, let's look at um, the energy first, and then we will introduce work. So first of all, let's introduce the energy concept. So the concept of energy is common. It's it's been used a lot of times in daily life, and we're not. We're very familiar with energy. Um, so every system in nature has a quantity. We call it total energy E. For example, in daily life, we're using a lot of energies. For example, when we drive the car, we're using the energy of gas. It's chemical energy. And when we use let's say, the light, we're using the electric energy. And for example, um, let's say, when we are running or when we're jumping, actually, we're using the energy stored in the body. So we convert the chemical energy stored in our body into some other type of energy. For example, if you're running, then you convert the chemical energy in your body into kinetic energy. If you're jumping to a higher position, then you're converting the chemical energy into gravitational potential energy. So that's the concept of energy. So for any system, it may contain a lot of different types of energies. For example, it may have some energies like, let me change the pen. It may have some K, which means kinetic energy, gravitational energy, spring potential energy, thermal energy, chemical energy, and other energies. If you sum up all of the types of energies in the system, then that's the total energy of the system. So here we listed several important energies. The first type of energy is kinetic energy. It's energy of motion. For example, when you are driving a car, when the car is running in the highway, it has some energy. For example, if it hits something, it will damage it because it has some energy. This type of energy is kinetic energy. When you throw away, let's say, a rock when it's flying, it has the same type of energy, which is kinetic energy. Okay, the second type of energy is gravitational energy. The gravitational potential energy is stored energy associated with object height above the ground. For example, if you lift a book up, then when the book is positioned in the upper or higher position, then it has a higher gravitational potential energy. So the higher the object is, the more gravitational potential energy it gained. So third type of energy, elastic energy or spring energy. It's another type of potential energy. This energy is stored when a spring or other elastic object is stretched or compressed. And then thermal energy. The thermal energy is the sum of kinetic energy and the potential energy of the molecules in an object. So that's thermal energy. For example, when something is okay, so thermal energy is related to temperature. For example, when an object has a higher temperature, then it has higher thermal energy. That's thermal energy. Chemical energy. It's energy stored in the bonds between molecules. And the nuclear energy. So it's energy stored in the mass of nucleus of an atom. So nuclear energy could be huge. Um, so that's several types of energies listed in this class, and we'll introduce them one by one. Mm, okay, and energies, different types of energy, they could be transferred or transformed into each other in a system. For example, a kinetic energy could be transferred into potential energy, and they also can be converted or transformed into chemical energy, and they can also they can also be transformed back into each other. And all the types of energy could be transferred into thermal energy. However, thermal energy cannot be transferred back. Okay, so let's take several examples. Let's say from kinetic to chemical energy or chemical energy to kinetic energy. For example, um, we eat some food and those food are transferred into chemical energy into our body. We store chemical energy in the body and we can run. When we run, this chemical energy in our body is converted into, um, let's say, kinetic energy. And um, for example, kinetic energy can be transferred into gravitational potential energy. Um, let's say if you throw or toss up a rock, when the rock leaves your hand, actually it has an initial speed, and when it's going up and up, so the initial speed is getting lower and lower, means the kinetic energy is getting lower. However, the position of the rock is getting higher, means the gravitational potential energy is getting higher. So this is the kinetic energy converted into potential energy. And for other energy types, they can also be converted into each other or transformed into each other. But for thermal energy, the types of other energies could be converted or transformed into thermal energy, but the thermal energy cannot be transferred back. And the total energy of the system equals to all the types of energy, um, the total of all the types of energy. So that's why it's called total energy. Okay, so when the weightlifter is lifting some weight, actually she or he is converting the chemical energy into gravitational potential energy. And here, elastic potential energy for the springboard is converted into kinetic energy. That's some examples. Now, let's see a quick check. A child is on the playground swing, motionless at the highest point of his arc. What energy transformation takes place as he swung back down to the lowest position of his motion? So what is your choice? Okay, so let's see. The answer is gravitational energy converted into kinetic energy, because when the swing, let's say, is swinging from the highest point to the lowest point, it's getting faster, but the position is getting lower. So the gravitational energy is converted into kinetic energy. There's some other examples. You can do it by yourself. Try to understand it. It's not very difficult. Okay. Now, energy transfers and work. Energy can be transferred between a system and its environment through work and heat. For example, if we have a system here, in the system it has several types of energy, and the total of all of these types of energies are total energy. And the system can um, flow some heat or can do some work to the environment That is called heat and work. So here we introduce the concept of work. Work is the mechanical transfer of energy to or from a system by pushing or pulling on it. And another concept is heat. So heat is easier to understand. Heat is a non-mechanical transfer of energy between a system and environmental due to a temperature difference between the two. For example, if your system has a high temperature and the environment has a lower temperature, the heat will flow from the high temperature system into the low temperature environment. That's heat flow. And if the system is growing bigger and bigger and pushing out its boundary, then it's doing some work to the environment. That's work. Okay, now let's see energy transfers and work. The athlete does work on the shot, giving it kinetic energy, which is K. So the athlete is pushing this ball. When it's pushing something, it's doing some work to this object. So this work will be converted into kinetic energy in this example. Now let's see the match. The hand does work on the match, giving it thermal energy. So there are some pushing forces on the match, and this force is doing some work on the match. And this type of work is converted into energy, which is thermal energy, because it's making the temperature of the match higher. When it's high enough, it will burn. Okay. In the last figure, the boy does some work on the slingshot, giving it elastic potential energy. So when it's pulling this rock, actually it's doing some work, and this type of work is converted into the spring energy of the slingshot. Okay, now let's see another example. A tow rope pulls a skier up the slope at constant speed. Now let's say this is a skier on the sled, and there is a towing rope which is towing it up. So during this process, what energy is transferred into what other type of energy? Okay, actually, the rolling tope is doing some work, and this type of work is making the position of the skier higher and higher, which means it's converted into potential energy, gravitational potential energy. And also thermal energy. Okay, we'll learn why it has some thermal energy, because there are some frictions. When there's some friction happens on the surface, some energy will be generated, which is thermal energy. That's why when you scratch your hand, you will feel it's getting warmer, because there's some frictions between your hands. So if you let's say scratch the hands, you will feel, or rub your hands, you will feel it's getting hotter. So because the work has been converted into thermal energy. Okay, so the work represents energy that is transferred into or out of a system. The total energy of a system changes by the amount of work done on it. So work represents, let's say, the change of energy. So the total energy change could be called the energy. Okay, so the equation for this is written here. The change of energy, delta E, equals the work. And it also equals the sum of the change of all the different types of energy. The work can increase or decrease the energy of a system. If no energy is transferred into or out of system, then that is isolated system. Okay, so there are some examples, so you can do it by yourself. The law of conservation energy. The total energy of isolated system remains constant. So here it's system. If the system is isolated, then the total energy is a constant. So if the system is constant, that means there is no work done by the system, or no work is done by the environment to the system, and there's no heat flows out or into the system. Okay, now we have learned something about the work. Now let's see how to calculate the work. So work is done on a system by external forces, the force outside the system. For example, now if there's a surfer on the surface of the water, and the wind is pushing the surfer, and the force is F, then the force is doing some work by pushing it using the force F by a distance of d, or displacement of d. So the force of the wind does work on the system, and due to this work, then the energy of the system is getting greater. So the work has been converted into the kinetic energy of the surfer. And the work can be calculated in this equation. Work equals to Fd, force times displacement. If the force F is in the direction of displacement. Let's see this previous example. The direction of force is going to the right, and the displacement of the surfer is also going to the right. So the force and displacement, they're in the same direction. Then the work could be calculated using this equation. Work equals to F times D. Although both force and displacement are vectors, work itself is a scalar, and the unit of work is joule. 1 joule equals to 1 Newton times meter. Now let's see one example here. Sarah pushes a heavy crate 3.0 meters along the floor at the constant speed. She pushes with a constant horizontal force of magnitude of 70. How much work has she done to the crate? Okay, so calculating work, it's very easy. We can use this equation. Work equals to Fd. So what is F? 70. What is D? 3. And the work could be calculated using that equation, F times D, because F and D, they're in the same direction. When they're in the same direction, you can use work equals to Fd, which is 210 joules in this example. Okay, so we have learned how to calculate the work when the force and displacement are in the same direction. Now let's see some other general cases when the force is at an angle to the displacement. Only the component of the force in the direction of displacement does work. For example, now we have a device like that to use the force of wind to push the cart. And the pushing force is going up and right. How to calculate the work? First, we can decompose the force into x direction and y direction. So the displacement of this card is in the right direction, or in x direction. So Fx, or the x direction of the force, is parallel to the displacement. Then the work could be calculated by the parallel direction of force. In this example, Fx times d. D is in x direction. And it equals to Fd times cosine theta. Theta is the angle between the force and displacement. So if the force is at an angle theta to the displacement, the component of the force F, which does the work, is F cosine theta. Okay, so that's the equation of calculating work when the force and the displacement are in the angle. Now let's see different types of angles. When the angle theta is 0, then that means the force and displacement are in the same direction. Then theta equals to 0, cosine theta equals to 1, work equals Fd cosine theta, or Fd times 1, it's Fd. So this is the equation we learned here. When F and D are in the same direction, then work simply equals to F times D. So F times D, it's just a specific example of the general equation, which is Fd cosine theta, when theta is 0. When theta is less than 90 degrees, like that, then Fd cosine theta is a number between 0 and 1. So the work is positive. When theta is 90, then cosine theta equals to 0. Then the work is 0. When theta is greater than 90 degrees, like that, then cosine theta is a negative number. So the work should be a negative work. When theta is 180 degrees, means the direction of the force and the displacement, they're in opposite direction. Cosine theta, which is cosine 180, equals negative 1. So work equals to Fd cosine theta, which is negative Fd, which is negative number. So the sign of the work is determined by the angle theta between the force and displacement. Now let's see, a constant force F pushes a particle through a displacement delta R. In which of these three cases does the force do negative work? So which one do you think is correct? So now let's see the angle theta. This theta is greater than 90. This theta is greater than 90. And this theta is 0. When theta is 0, it's doing positive work. When theta is greater than 90, when it's greater than 90, then the work is doing some negative, the force is doing some negative work because cosine theta, which is greater than 90, it's negative. So the answer should be A and B, which is D. Okay, so which force below does most work? Okay, this question needs some type of calculation, but let's see what's the equation of the calculation. Work equals to F d cosine theta. So for this theta, it's 90 degrees. Cosine theta equals to 0. So for this force, it's doing 0 work. Okay, for this one, it's A, which is force, times D, which is delta R, times cosine theta. Cosine theta is cosine 60 degree, it's 0.5 times 0.5. That's the work done to this second system. And then for this force, theta is 0, so you have Fd. Cosine theta means 1, so Fd means 6 times d. Okay, so which one is greater? 8 times 0.5 times d, 6 times d. So the last one is greater. Okay, now let's solve another problem. A strap inclined upward at 45 angle pulls a suitcase through the airport. The tension is 20 Newton. How much work does the tension do if the suitcase is pulled 100 meters at a constant speed? Okay, now let's say we're going to calculate work. Work equals to Fd cosine theta. So what is F? F is 20. What is D? D is 100 meters. What is theta? 45 degrees. You just take all the numbers into the equation, you will find the answer. It's very easy. Okay, now, so we have done several examples of the work calculation. The equation is simple. It's Fd cosine theta. You just need to identify which is F, what is D, and what is theta. Then you can calculate it. So the calculation of the work is very simple. It's not complicated. Now, a force do not do work. So which type of force doesn't do work? A force doesn't do work on an object if, first, the object undergoes no displacement. Of course, if the displacement is 0, then the work is 0. Second, the force is perpendicular to the displacement. In this case, cosine theta is 0. Then there's no work done to the system. In the third situation, the part of the object on which the force acts undergoes no displacement, even if other part of the object is moving. So if the part of the object on which the force acts has no displacement, then d is 0, then there's no work done to the system. Okay. There's some quick questions. You can do it by yourself. Now, we have learned work, and then let's learn several different types of energies, learn how to calculate energy. First type of energy, kinetic energy. Kinetic energy is energy of motion. Kinetic energy could be in two forms, translational or rotational kinetic energy. In this class, in this course, we only consider translational energy. So here, for translational energy, the calculation equation is K equals to 1 over 2 mv squared. Here, m is mass, v is velocity or speed. So please keep in mind this equation. You will need it to do some calculations in your exams and homework. Now, ball A has half the mass and 8 times the kinetic energy of ball B. What is the speed of ratio VA over VB? So it's you're going to use the equation shown here. Kinetic energy equals to 1/2 mv squared. And then using that equation, how to calculate the speed ratio. Please try to do it by yourself. Rotational kinetic energy, we're not going to talk about that because it's optional. You can learn it by yourself. It's not going to be part of our homework or exam. A two-man bobsled has a mass of 390 kilograms. Starting from rest, the two racers push the sled for the first 50 meters with a net force of 270 newtons. If there's no friction, what's the sled's speed at the end of the 50 meters? Okay. Now the two men are pushing the sled, which is doing some work. We have learned the change of energy is the work. So we can calculate the change of the energy, which is the work, by using work equals to Fd cosine theta, but here theta is 0 because the force and displacement, they're in the same direction. Cosine theta is 1, so work equals to Fd. And work equals to the energy change. In this case, at the beginning, there is no energy on this sled, but at the end, the energy has been changed into kinetic energy. So it equals to energy change. In this case, it's kinetic energy, or final energy, subtracted by initial energy, which is 0. So it's still kinetic energy. So, do you know F, the pushing force? Yes, it's here. Do you know the displacement? Yes, it's here. Do you know the kinetic energy? We don't know, but we know the equation to calculate it, which is 1/2 mv squared. So m, you know m here. The only thing you don't know is v, and you want to calculate v. You know Fd, you know m, you don't know v, then you can calculate v by using this equation. Okay, so finally you will get the answer here. Okay, some other quick test. Okay, potential energy. Now, let's see, what is potential energy? Potential energy is stored energy that can be readily converted into other forms of energy, such as kinetic energy or thermal energy. Forces that can store useful energy are conservative forces. It could be gravity, it could be elastic forces. So forces such as frictions that cannot store useful energy are non-conservative forces. First, let's see the gravitational potential energy. The change in gravitational potential energy is proportional to the change in its height. Now, if we lift the book from some position to a higher position, we can calculate the work. First, the pushing force equals to the weight, which is mg, and the work could be calculated by Fd. So F equals to the weight, which is mg, d is a displacement, which is delta y here. So that's the work that has been done from here to there. It's mg delta y, or mgy. So this work is completely converted into the gravitational potential energy. So the gravitational potential energy is calculated by mgy. We can choose the reference level where gravitational potential energy Ug equals to 0, since only changes in Ug matter. So because gravity is conservative force, gravitational potential energy depends only on the height. It's independent to the path. So let's say for this man, if he's going to the hill, going up to the hill, in the path A or path B. So no matter which path he's using, the change from the top position to the bottom position, it's the energy is the same. So the gravitational energy is the same. It's independent from the path. It only depends on the position or the height. Okay, now let's see this example. Rank in order from largest to smallest the gravitational potential energies of the balls. Let's see which ball has the largest gravitational potential energy. Which one has greatest? The answer is this one. So the gravitational potential energy depend only on the height. So the third ball is highest, so it has the highest energy. And the second and the fourth, they have the same height, so they have the same energy. And for the first one, it's the lowest, then it has the lowest potential, gravitational potential energy. Starting from rest, a marble first rolls down a steeper hill, then down a less steep hill of the same height, for which is going faster at the bottom. Now you have 4 options, A, B, C, and D. So which one do you think is faster? The answer is C, the same speed, because at the beginning they have the same amount of total energy, which is a gravitational potential energy. And when they reach the lowest position, the gravitational potential energy has been converted into kinetic energy. So they will have the same kinetic energy, then they will have the same speed. Okay, a small child slides down 4 frictionless slides from A to D. So rank in order from largest to smallest her speeds at the bottom. Okay, so which slide may give her the largest speed at the bottom? The answer is D again. So it doesn't matter what path this kid is taking. It only matters the height. So if at the beginning the height is the same, then the original gravitational potential energy at the beginning is the same, and then it will be converted into the same amount of kinetic energy. So the velocity or speed should be the same. Okay, elastic potential energy. The elastic potential energy is stored when the force compress a spring or stretch a spring. Hooke's law describes the force required to compress a spring. And this type of elastic potential energy could be calculated using this equation. The energy equals to 1/2 k x squared. So here k is the constant, the spring constant, or Hooke's constant. It depends on different types of spring. For some spring, it's harder, then this k is a greater constant. For some springs which are very soft, then the k is a smaller number. X is the, let's say, the distance from the equilibrium position. Okay. 3 balls are thrown from a cliff with the same speed but at different angles. Which ball has the greatest speed just before it's hitting the ground? Okay, so which one do you think is the greatest? The answer is D. No matter if you're tossing up and down or horizontally, the initial energy is the same. At the beginning, the initial energy is only the kinetic energy. the speed is the same, so they have the same amount of kinetic energy. And then at position ABC, there's some gravitational potential energies gained, but they gained the same amount of gravitational potential energy. So the total energy at the end should also be the same. That's the kinetic energy at the beginning plus the total energy or plus the gravitational potential energy. So it's the same. So here's another example. So please do it by yourself. Now let's see another example. An archer pulls back the string on her bow to a distance of 70 centimeters from its equilibrium position. To hold the string at this position takes a force of 140 Newton. How much elastic potential energy is stored in the bow? Okay. Um, so Hooke's law tells us F equals to K negative Kx. So we can calculate the K here. If the force is 140 and the displacement is 0.7 meters, then you can calculate K. Once you have K, you can calculate the elastic potential energy, which is 1/2 K x squared. So you have x, you have K calculated, then you can calculate the elastic potential energy. So here's the details of the calculation. Thermal energy. Thermal energy is the sum of the kinetic energy of atoms and molecules in a substance and the elastic potential energy stored in the molecule bonds between atoms. So for hot object, it has higher thermal energy. For cold object, it has a lower thermal energy. So thermal energy depends on the temperature. For example, for a hot temperature object, if you zoom in to look at the microscopic view of the, for example, the ion, you will see the molecules are performing like that. The molecules are like beads connected by springs, and the beads are vibrating, so they're moving. If it's hot, then they're moving fast, and they could be away from their equilibrium position a lot. So you see the springs means the bonds between molecules. It could be stretched or compressed a lot. If the object is cold, then the velocity of the molecule is less, and the molecule cannot be too far away from the equilibrium positions, so the springs are not compressed or stretched much. So that's thermal energy. It simply depends on the temperature. And the temperature is a macroscopic feature of an object. In the microscopic feature, it means the spring energies for the bonds and kinetic energies for the beads or atoms or molecules. So here, the friction on the moving object will do some work. That work will create thermal energy. So if you use a thermometer or thermal camera to take a picture when one box is moved on the surface of the ground and there are some frictions happening, then you will see the temperature on the path is higher because the friction is doing some work, and this work is converted into thermal energy, which makes the temperature of the surface higher. Okay, now a 0.3 kilogram block of wood is rubbed back and forth against the wood table 30 times in each direction. The block is moved 8 centimeters on each stroke and pressed against the table with a force of 22 newtons. How much thermal energy is created in this process? Okay. Um, Now, first of all, the thermal energy is created by the uh, uh, the force or the work. So the work which is done from the friction is converted into thermal energy, as we learned in previous slides. Um, then this question becomes how much work has been done by the friction. Okay, so first we need to calculate the force of friction and then times the displacement. Then you will get the work. Can you calculate the force of friction? Do you remember the equation? Friction equals to mu k, mu n, sorry. N is the pressure. Um, and the mu is a constant. And this mu is the kinetic friction coefficient of wood to wood. It's 0.2. And then if you know mu, which is 0.2, and you know n, then you can calculate the force. If you know the force and you know the distance or displacement, then you can calculate the work. Then you solve the problem. Okay, now let's see what's n. If you do a free body diagram on this block, you will see it has three forces: the weight of the block, the pressing force, and the normal force. The normal force need to balance those two forces. So normal force equals to W plus F, which is the weight plus the the normal force could be calculated, and then if you have normal force times the mu, then you have the friction. Then you use friction times the distance, you will get the work has been done or the work has been converted into thermal energy. Okay, so N equals to W plus F, which is here, and the friction is F times delta X. So um, F is here. It's mu times N. F times delta X. X is 2 times 30 times 8 meters because each stroke is 8 meters and each round of stroke is two strokes, and you do it 30 times, so it's 2 times 30 times 8 centimeters. Finally, it's 4.8 meters. So finally, you can calculate the work. It's 24 joules. This is the amount of energy has been converted into thermal energy. Okay. The law of conservation of energy. We can use the law of conservation of energy to develop a before and after perspective for energy conservation. So the total energy change equals to the work. Total energy change could be written into the sum of all the other type of energies. In the isolated system, there's no work has been done to the system. So the change of total energy is 0. Then final energy equals to the initial energy. Okay. There's some examples. You can do it by yourself. It gives you some hint to help you to solve the questions. So it's not difficult. You just need to spend some time to understand it. Okay, now let's see this example. A child slides down the slide at a constant speed of 1.5 meters per second. The height of the slide is 3 meters. Write down the equation for the conservation of energy, noting the choice of system, the initial and final states, and what energy transfer has been taken place. Okay. So you can take this as a practice, and let's solve a problem together for this example. While at the county fair, Katie tries a water slide here, whose shape is shown here. The starting point is 9.0 meters above the ground. She pushes off an initial speed of 2 meters per second. If the slide is frictionless, how fast will Kate be traveling at the bottom? Okay, so in this example, the keyword is frictionless. So there's no friction. Then there's no thermal energy generated. So at the bottom, it will be faster because the gravitational potential energy has been converted into kinetic energy. So the key is gravitational potential energy here has been converted into kinetic energy here. So can you calculate the initial total energy? Because the initial total energy should be equals to the let's say the final total energy. So for initial total energy, it has kinetic energy. It also has some gravitational potential energy. For the final energy, it has only kinetic energy. Okay, for initial energy, it's 1/2 mv initial. And for the initial gravitational energy, it's mgy. Sorry, this is y initial. For the final kinetic energy, it's 1/2 mv final. Now let's see. Do you know m? We don't know. Do you know v initial? Yes. Initial speed is 2. Do you know y initial? Yes, it's 9 meters above the ground. Sorry, it's mv squared here, and mv squared, because kinetic energy, so it's 1/2 mv squared. But you don't know m. However, the m will be cancelled because each term has an m. So finally it becomes 1/2 v initial squared plus gy plus equals to 1/2 vf squared. You know v initial, you know g, you know y initial. The only number you don't know is vf, so you can calculate it using this equation. Same thing here, so it equals to the square root of this term. Take the numbers in, you get the answer, which is 13 meters per second. Okay, now let's solve another problem together. Monica puts her daughter Jessie in a bike trailer. The trailer and Jessie together have a mass of 25 kilograms. Monica starts up a 100-meter long slope that is 4 meters high. On the slope, Monica's bike pulls on the trailer with a constant force of 8 newtons. They start out at the bottom of the slope with the initial speed of 5.3 meters per second. What's their speed at the top of the shape? Okay, it's similar to the previous question. However, it's been doing some work to the system. So first of all, the law of energy conservation, the work equals to the delta E, or E final subtracted by E initial. So can you calculate the work? Work equals to FD. Sorry, it's FD, it's not. Oh, let me erase it. So it's FD, which is work, equals to E final subtracted by E initial. So what is F? The F is 8 Newton. What is D? It's 100 long. Okay. And now let's see, what is EF? The final energy is gravitational energy because it's getting higher by 4 meters. Plus K final, the final kinetic energy, equals to subtracted by initial energy. So what is initial energy? It's K initial. So at the beginning, it has some initial speed, so it has some initial kinetic energy. So UG means mgy plus kf. Kf is 1/2 v final squared subtracted by k initial. It's 1/2 mv initial squared. You know F, you know D. Do you know M? Yes. The M is 25 kilogram. Do you know G? It's 9.8. Do you know Y? It's 4. You know M? Do you know V final? No, we don't know. That's the question. Do you know V initial? Yes. It's 5.3. So you know everything except VF, or final speed. So you can calculate final speed using the equation if you take all the numbers into the equation. So here shows a more detailed way of the calculation. But basically, this is the same thing I'm writing on the below the question. So take all the numbers in, you will get the answer, which is this number. Okay, energy in collisions. A collision in which the colliding objects stick together and then move with a common final velocity is perfectly inelastic collision. A collision in which mechanical energy is conserved is called a perfectly elastic collision. So while momentum is conserved in all collisions, mechanical energy is only conserved in a perfectly elastic collision. In an inelastic collision, some mechanical energy is converted into thermal energy. Now, let's see one example here to explain what happens in the inelastic collision. Now, this figure shows two train cars that move toward each other, collide, and couple together. In this example, we use conservation of momentum to find the final velocity shown in the figure from the given initial velocities. How much thermal energy is created in this collision? So, if the initial velocity is 1.5 and negative 1.1 for the two cars, after they collide, they stick together and move in the same speed. So we can calculate the final speed if we know all the initial speeds using the conservation of momentum. So what we have learned in the previous slides. Then you will calculate the V final is this number. And let's calculate the initial kinetic energy, and the final kinetic energy. Initial kinetic energy could be calculated by 1/2 mv squared plus 1/2 m2 v2 squared, which is this number. And the kf, the final energy, is 1/2 of the total mass times final velocity, because they stick together, so they have the same speed. So that's this number. So you will see the initial kinetic energy and the total kinetic energies are completely different. So it's losing a lot of energy, kinetic energy, from the initial to the final states. Actually, the energy is not lost. It's just being transferred into another type of energy, which is thermal energy. That's why when something hit another thing, for example, if there are two cars hitting each other, then after a car collision, the temperature of the car is really high, because some other type of energy, usually it's kinetic energy, has been converted into thermal energy, which makes the temperature of the collision objects to be high. So in this example, over 90% of the initial kinetic energy is transformed into thermal energy. This is typical of real-world collisions. Now let's see elastic collision. For elastic collision, it obeys conservation of momentum and the conservation of mechanical energy. There is no thermal energy happened. There is no thermal energy generated. So for example, if the first ball hits the second one, so they will have a collision, and then they will have their final, let's say, velocities, and the momentum could be calculated in this way. Initial momentum is just the momentum of ball 1. Final momentum is the momentum of ball 1 and ball 2. Energy, this is the initial kinetic energy of ball 1, final kinetic energy of ball 1 plus ball 2. So if it's elastic collision, these two terms are conserved. The momentum is conserved and the energy is conserved. Okay, so on the air hockey table, a moving puck traveling to the right at 2.3 meters make a head-on collision on an identical puck at the rest. What's the final velocity of each puck? So it's let's consider it to be an elastic collision. For elastic collision, the momentum is conserved and the energy is conserved. Then we can use this equation and this equation. Let's write down both of the equations, and then you can calculate the speed from these two equations. Here, m1 equals to m2 because they're identical. Then finally, after solving the equations, you will get something like that. So the incoming puck will stop dead, and the initial stationary puck goes off with the same velocity that the incoming one had. A bike helmet, basically a shell of hard, crushable foam, is tested by being strapped onto a 5 kilogram head foam and dropped from a height of 2 meters onto a hard anvil. What force is encountered by head foam if the impact crushes the foam by 3 centimeters? Okay, so when this test happens, so it falls down from a distance, and here, after it hitting the ground, the force from the foam is pushing up, and it's doing some work. So the force is doing some work by a distance of d, and we know this distance is 3 centimeters. So these 3 centimeter, and this work will, let's say, will be the change of the energy. So the change of energy is from here to there. The change of energy is the gravitational potential energy. At the beginning, it has high gravitational potential energy. At the end, it doesn't have this potential energy. So the potential energy has been changed into um, the has been changed, and also the initial kinetic energy has also been changed because at the end it doesn't have any um, um, energy, mechanical energy, or it doesn't have any potential energy and kinetic energy. Now, still work equals to delta E, which means E final subtracted by E initial. For E initial, what's the E initial? It's 0 because at the end it doesn't have kinetic energy or potential energy. What's E? Sorry, E final is 0. What is E initial? E initial is um, UG, gravitational potential energy, plus K, which is kinetic energy. So can you calculate UG? Yes, you can use mgy. Can you calculate kinetic energy? Yes, it's 1/2 mv squared, and v is 0. So at the beginning, it doesn't have kinetic energy, or the kinetic energy is 0. So the UG has been or gravitational energy has been converted completely into the work. Okay, so work equals to UF subtracted by U initial. UF is 0. Then becomes U initial. So you can calculate U initial. It's mgy. So mgy, it's the U initial. Work is FD, so F equals to mgy over D. So finally you get this number. Okay, so that's a lot of practices of work and energies. Now let's see power. What is power? Power is the rate at which the energy is transformed or transferred. The equation of calculating power is delta E over delta T. Or when some force is doing some work, you can use work over delta T because work equals to the energy change. So that's the definition of power. The unit of power is watt, or joule per second. A force doing work transfers energy. The rate that this force transfers energy is the output power of that force, which can be calculated by W over delta T. However, W equals to F displacement delta X. Delta X over delta T equals to V. So sometimes the power could be written in this form, P equals to FV. Okay, so there are some questions. You can do it by yourself. Now let's solve this equation together, this problem together. Your 1,500 car is behind a truck traveling at 60 miles per hour. To pass the truck, you speed up to 75 miles per hour in 6 seconds. What engine power is required to do this? Okay. Now let's see. We're going to calculate engine power. Power equals to W over delta T, or delta E over delta T. So the delta T is 6 seconds. Do you know the delta E? Delta E equals to E final subtracted by E initial. How to calculate E final? At the end, at the final state, it has speed of this. That's the speed. Can you calculate the energy, which is the kinetic energy? The answer is yes. It's 1/2 mv squared. Can you calculate the initial energy? The answer is yes. It's 1/2 mv squared. So you know initial speed, final speed, then you can calculate initial kinetic energy and the final kinetic energy. Then you have the delta E over delta T, you will get the power. Initial kinetic energy, final kinetic energy, delta K or delta E, then you get delta K over delta T, you get the P. The power is 53,000 watts. Okay, so that's everything in chapter 10. Thank you. I'll see you. Okay, so that's the end of the chapter 10. We don't have any other chapters. So that's the end of this course. Thank you.